In today's lesson, we will be extending the inverse trig functions to include the reciprocal functions, as well as evaluate some inverse trig functions for values that are not on the unit circle, and then we will compose some of our trig functions. Notice down here in this table, you can see an example of a composite trig function and an inverse function. Also in this example, 15 over 17 is not a value that we see on the unit circle. So we have to do a little more math in order to actually evaluate this. Let's start with something that we know. We know that cosecant and sine are reciprocals, as well as secant and cosine, and cotangent and tangent. Here's an example of how we can use what we know about composite functions, as well as inverse functions, to derive the reciprocal of the inverse sine function. When we take an inverse, remember that our first step is just to switch x and y. So in this example, we want to take the inverse of the inverse sine of x. So we switch x and y. If we change the sign to cosecant, then we also have to take the reciprocal of x, because remember, this is a reciprocal function. If I multiply both sides by inverse cosecant, look what happens here. Our cosecant disappears, and that's because of what we know about taking the composite of a function. So here we have a function, and it's composed of its inverse. Out pops x. We can also take the inverse and compose it with its function, and again, out pops x. So if we multiply both sides by inverse cosecant, out pops y. And now we know y up here was inverse sine of x, so now we have proved that the inverse cosecant of 1 over x is equal to the inverse sine of just x, or vice versa. This works for both cosine and tangent and its reciprocal functions as well. The other thing that we need to consider is tangent and cotangent, and their different domain restrictions. Notice the black line is our tangent, the red line is our cotangent. When we are restricting the domain in order to have an inverse, we restrict those differently. Let's look at an example. In this top one, we have tangent. In order to have just this leg, because we need only one leg, otherwise it doesn't pass the one-to-one test or the horizontal line test, we restrict the domain for tangent to between negative pi over 2 and positive pi over 2. Whereas cotangent, if you'll notice the way it's graphed, reflected and shifted, we end up restricting the domain between 0 and pi. And I will show you how that impacts how we evaluate tangent and cotangent. So to sum it up, remember these relationships. We can take and turn cosecant into sine by just taking the reciprocal of our x value. We can do that with cosine and tangent. Also remember that tangent has a domain restriction between negative pi over 2 and positive pi over 2, and cotangent goes between 0 and pi. All right, let's apply what we know. Go ahead and pause the video and see if you can evaluate the inverse secant of root 2, the inverse cotangent of negative root 3, and the inverse cosecant of 2 root 3 over 3. Looking at our first example, I will switch secant to its reciprocal function of cosine, which means I need to take the reciprocal of root 2. And then, in order to properly evaluate it, I need it to look rationalized. So when I rationalize the cosine, inverse cosine of 1 over root 2, I end up with the cosine of root 2 over 2. If I want to determine at what angle, sorry, this is the inverse cosine, if I want to determine at what angle inverse cosine has an exact value of root 2 over 2, I know that's pi over 4, or 45 degrees. This value is positive, and cosine has a restricted value between 0 and pi, so this is in quadrant 1. For the second example, we would do exactly the same thing. We would switch it to its reciprocal function, and now let's rationalize. When we rationalize, we can recognize that the inverse tangent of negative root 3 over 3 is going to be down here. Remember that tangent has a domain restriction between pi over 2 and negative pi over 2. So we can rotate up into quadrant 1, which has all positive values, or we can rotate down here into quadrant 4. Well, we know this is 30 degrees or pi over 6. Here's the problem, and here's where it's tricky. Tangent has a different domain than cotangent. Remember what we're looking for. We're actually looking for the inverse cotangent, but what angle do we have an exact value of negative root 3? Well, negative pi over 6 does not fall within the domain of cotangent between 0 and pi. So what can we do about that? Well, cotangent is going to be negative here in quadrant 2. So our angle will actually need to fall here. How do we get there? Well, if you look, that's half of a rotation, or pi. We can just add pi to negative pi over 6 to get 5 pi over 6. And that is what this angle rotation is. So if we start at the origin and rotate around, we stop at 5 pi over 6. And that's where we get an exact value of negative root 3 for cotangent. So our answer is 5 pi over 6. Always be careful when you're dealing with cotangent and tangent and you're working between the two due to this different domain restriction. How about the last problem? For this problem, we'll do exactly the same thing. Switch it to its reciprocal function because we know these values, but then we need to take the reciprocal of x, which is 3 over 2 root 3. In order to rationalize this, we just need to multiply by the radical that's in the denominator, which is root 3. And that gives us 3 root 3 over 2 times 3. If we simplify this a little more, the 3's cancel and we end up with root 3 over 2. So we need to find the angle for which sine has a value of root 3 over 2. And we know that angle already. That's 60 degrees or pi over 3. Since this is positive, we know that we fall into quadrant 1, and that is in fact our answer. Let's go ahead and explore now some composite inverse trig functions. These are not difficult as long as you consider that you need to move from the inside out. So when we're solving this function, we're actually going to take the sine of whatever this inside amount turns out to be. Well, the angle at which sine is root 2 over 2 is just pi over 4. And the sine of pi over 4 is root 2 over 2. Notice what happened. If we go back to our inverse functions and we compose them, out pops this x. And that's exactly what's happening here. Out popped root 2 over 2. We just need to be conscientious, though, when we're dealing with cotangent and tangent to make sure that, in fact, we're in the right quadrant. How about this next example? Here we need to figure out at what angle does tangent equal positive root 3, and we know that's 60 degrees or pi over 3. The cosine of pi over 3 is just 1/2. And finally, our last problem, where does inverse cosine have an exact value of negative 1/2? Since cosine is in quadrants 1 and 2, we know negative 1/2 is going to be here in quadrant 2. Well, at 1/2, cosine has an exact value of 1/2 at 60 degrees, or pi over 3. So, if this is 1 pi over 3, then this right here has to be 2 pi over 3, or 120 degrees. So we need to find the sine of 2 pi over 3. Well, in quadrant 2, the sign is positive, and we know that the sine of 2 pi over 3 is going to be root 3 over 2. So remember, with these, work from the inside out. Let's compose using our inverse reciprocal trig functions. Go ahead and pause the video and see if you can do this on your own. For our first example, remember, we're going to solve the inside first, so switch that to tangent. And when we rationalize, we end up with the inverse tangent of root 3 over 3. Well, this is positive, and we know that both cotangent and tangent share quadrant 1, so we don't need to worry about our domain here. Well, where is the tangent equal to root 3 over 3? That's at 30 degrees or pi over 6. Now we're safe to evaluate what is the cosine at pi over 6, we know that is root 3 over 2. For our second one, we know that cosecant of pi over 3 is going to be the same thing as the sine of pi over 3, but then we're going to flip our exact value. Remember, take the reciprocal. So in fact, the cosecant then would be 2 over root 3, which I'm going to leave like that for now and not rationalize, because look what I have here. I have to now find the inverse secant of 2 pi over 3, which we know is going to be the same thing as the inverse cosine of the reciprocal of this, root 3 over 2. Well, root 3 over 2 is 30 degrees, so inverse cosine has an exact value of root 3 over 2 at 30 degrees, or pi over 6. Again, not too difficult if we just take it one step at a time. Do the inside first, and then the outside. How about the last one? This one's easy. We're not dealing with any reciprocal functions. So the inverse cosine of root 2 over 2 has an angle of pi over 4, and then the sine of pi over 4 is just root 2 over 2. Let's go ahead and conclude with some composite functions with values that are not directly on the unit circle. Let's look at how we would solve this. Again, we're still going to use the inside and work our way out. So we want the inverse sine of 3 over 5. Well, 3 over 5 is an exact value, and we know since it's positive that it will be in quadrant 1. I can draw my triangle here in quadrant 1 with my theta here, which I'm trying to find, and then I can label. Sine is opposite over hypotenuse. So this is 3, and this is 5. I can use Pythagorean theorem to get this value, but I can see right away that this is a 3, 4, 5, or Pythagorean triple. So I know that side is 4. Well, in this case, I know then that I want the cosine of this angle. So the cosine of the angle is adjacent over hypotenuse. In this case, my answer would then be 4 over 5. I never really had to find this angle in order to find my end result. I just had to sketch it out in order to help me find the cosine. How about the second one? Pause the video and see if you can sketch this out and solve to find the tangent of this angle. Well, here's what I got. We want the inverse sine of the exact value of negative 3/4. Since it's negative, we're down here in quadrant 4. If I sketch it out, opposite over hypotenuse, I know the opposite here is going to be negative because I'm dropping into the negative for y. What is my x value? Well, I can use Pythagorean theorem here to determine that my x value is root 7. Now I'm in a great position to find the tangent of this angle. Tangent is opposite over hypotenuse, so that's negative 3 over root 7. Of course, I would need to rationalize my denominator, and I would get negative 3 root 7 over 7. So remember, these composite functions are not difficult if you just work from the inside out. And if you have an exact value that's not a common value on your unit circle, you can sketch it out in order to define this angle and then find the outside trig function by evaluating it at that angle. That concludes our lesson on inverse trig, reciprocal, and composite functions. Now you're able to extend the inverse trig functions to include these reciprocal functions, as well as evaluate functions that are not on the unit circle and evaluate inverse composite trig functions.